see you all came out tonight. Thank you for that. As Mary said, my name is Steve Hilbert. I am a climatologist / meteorologist with the Midwestern Regional Climate Center, which is associated with those other 3 institutions up there. I was director until about 2 years ago, and I retired, semi-retired now. I like to say I'm doing the fun stuff now. I don't worry about any administrative stuff. I don't have to stay after 5 o'clock. That's all part-time. So yeah, a lot saved for semi-retirement. So at any rate, this presentation is largely going to revolve around clouds. And I guarantee you there's probably a lot here you've never known about clouds. Actually, as I put together this presentation, the first time I did it, there's a lot I learned about clouds, and I've been in meteorology my whole life. But to be honest, clouds are not something you don't take a class on clouds in meteorology. You take a class on dynamics and fluid dynamics and atmospheric electricity and all the theoretical things, but you don't take anything on clouds or some of the practical weather aspects. You sort of learn that on your own. And depending on how far you want to delve into it, depends on how much you know. So actually I learned a lot putting together this presentation about a year ago. So what we're going to cover tonight, that's good. Turn it on. Are several things. We're going to talk about basics of clouds. I think everybody knows the absolute basic. They're all made out of water droplets, or most of them. Cloud classification, a little bit more about types and detail. Some clues in the sky you can use to quote forecast, at least short term. Some indicators of clouds and storm behavior, and then a little bit about precipitation. And Mary mentioned COCORAS, which stands for the Community Collaborative Rain, Hail, and Snow Network. Some of you have probably seen me do a presentation on that before. I will make a little pitch for that at the end of this, but it will only be a minute or two. So if you're interested in weather, this is the topic for you all the way through. So when I went to school, I was in undergrad school I graduated in 1974. We were still getting weather observations over what they called circuit A teletype. We had the teletype machine there, printed out reams and reams of paper. We had some satellite images you could get maybe once or twice a day. The models were pretty rudimentary. They went out only 36 hours, and there were 2 of them. And they weren't all that great, but they're okay. We didn't have access to the radar data you can pretty much get on your smartphone now. There was a lot. I mean, you had to learn basic weather and weather forecasting by knowing basically the theory behind it and some practical applications. We didn't have the menu of models and all the technology we have to today. We had satellites that give us different images of the Earth. This happens to be a water vapor image. You get visible images, infrared images. We get hemispheric images. We get global images. We had images all over the place. We have radar now, as I said, you can get on your smartphone. That's very sophisticated. We have maybe a half a dozen reliable short to midterm forecast models we can look at. Some that go out 16 days. Now, how accurate they are at 16 days is usually not that great, but we get an idea of what the patterns are like. And so we have a lot of tools at our disposal now that we didn't have even 15 years ago. But underlying this whole thing, including the models, is weather observations. If we don't have observations of what is currently happening in the weather, you can't initialize those models to run correctly. You've heard of the term garbage in, garbage out. Well, if you have bad observations going into models, you get bad results. So observations are key. And unfortunately, probably, there used to be a joke about meteorologists working in windowless rooms and that type of thing, but we all want to work in a room where you can see what's going on outside. A lot of enthusiastic forecasters, at least at my age and maybe 20 years after, a lot of them got into it as kids. I mean, I knew at 10 years old that I wanted to get into this field. Now a lot of it's fueled by, they want to chase storms. You see what's going, you can see all the reality TV shows. Storm chasing, that looks exciting, but very few people make a living at storm chasing. So, and it's not easy to make a living in weather forecasting either, because there's only a limited number of jobs. So, we got radar. This is an image of, I forget which hurricane it is, but it's probably New Orleans.
Katrina?
Katrina. Yes, that's Katrina before landfall, I believe it is. And that, I mean, anybody can pull that up now. You can sit at home on your computer and watch live radar of the latest hurricane that you want. And these are, that's an example of what some of the model output looks like. It looks like a lot of mess, but those lines mean something. All that green is precipitation. So we get down to Ben Franklin. This is attributed to Ben Franklin. I've heard various versions of that, but some people are weather-wise, but most are otherwise. And everybody pays attention to the weather. I doubt there's a day goes by when somebody you know doesn't mention something about the weather, including you, because it affects us in our everyday lives. What we decide to get dressed in the morning depends on what the weather's going to be. Maybe we decide whether we take a trip or not, how we dress the kids, whatever. So we all pay attention to the weather, maybe not so overtly as some of us other students. So first of all, in the atmosphere, water vapor is really the key. It comprises a small percentage of the atmosphere, but it really marks everything. This is a water vapor image, and it's sort of a false color image. Those colors are attributed to certain wavelengths, but it's one of my favorites because you can actually see a lot of the features in the atmosphere. You see right here is an upper level low. You can see the counterclockwise spinning here. Here's another one up here, although this is a general ridge pattern. You see this orange is very dry air. The blues and greens are very moist air. And in between, this is dry air too. The darker colors are dry air. But in the absence of anything else, you can get a pretty good idea of what's going on in the atmosphere up to about 20,000 feet or so, because that's imaging all the water vapor. So water vapor, a lot of this water vapor is not visible as clouds too, by the way. So it detects water vapor at very low levels. But the visible water vapor is clouds. And we can learn a lot about what's going on by paying attention to the clouds in the sky. So, again, I said it didn't account for very much in the atmosphere. It's 4% by volume, it's the water vapor, but it's a very important 4%. Most of it's contained within the troposphere, the lower troposphere, which is where all most of our weather occurs. And it's also a very key factor in how our weather works. Water vapor is less dense than dry air, which means it's unstable. Given it at the same temperature, it will tend to rise faster than dry air. And that's what we get, that what gives us the clouds. Clouds formed by condensation of water vapor, either through just that natural buoyancy or it's forced upward by some other mechanism, such as a cold front or some other way to lift the air. So you can see most of the clouds are here. That's roughly, probably most of them are going to be very tops of thunderstorms, might get to very extreme, get to 70,000 feet. A typical severe thunderstorm is probably closer to 50 to 65, but some of the big supercells, especially out in the plains in the west central U.S., can get up to 70, 75,000 feet. That is huge. But that below that level is where most of our weather occurs. And actually, some thunderstorms tops will actually shoot through the tropopause into the tropopause from the troposphere. So, how did we get cloud classification? We know about cumulus clouds, and most of you heard of cirrus clouds or stratus clouds. But how did we get that classification? Well, actually, it was developed by a chemist, of all things. In the early 1800s, he was a British chemist, and he just had a very large interest in the weather. And his name was Luke Howard, not Lucas, which I found very strange. It sounds very informal for 1800s England. A guy named Luke Howard, sounds like a basketball player. But there were several classification schemes that had been proposed already. A Frenchman had done one, and I think there was another one by a German. But because Howard based his Latin, it was more readily accepted because Latin was the language of science. And he did it like plant or animal taxonomy. If master naturalists, master gardeners, you know your plant and animal taxonomy, clouds are very much classified the same way. So we have a genus of clouds, And we're going to go through these. We have cirriform clouds. Those are the cirrus clouds. We have cumuliform, which are the puffy clouds. Cumulonimbus, which is the thunderstorm clouds. And then stratiform and stratocumuliform, which are more of the lower layer and tend to be the more, shall you say, nondescript clouds. They don't have much features to it. And then we have families of clouds: high clouds, middle clouds, low clouds, and then the vertically developing clouds like thunderstorms. And then there's stable and unstable clouds in each of these categories, and we'll talk a little bit about that. And then we have varieties of clouds. We have opacity-based clouds. You get that milky sky where you can see the sun through it, but you don't really get any sunlight. You get pattern-based clouds. You see waveforms in the clouds. That tells you a lot about what's going on with the winds in the upper atmosphere, or at least at that level. We have different combinations of clouds. One of the things you learn about in storm spotting is accessory clouds. It's not like trying to dress a storm, but there's little types of clouds that develop with certain types of storms that are telltale, and we'll talk about some of those. Then we have precipitation-based clouds. Those are the nimbus clouds. And then we have cloud-based varieties as well. Now, I'm just not going to go through these in detail, but you can see, if you can read this, the variety that the species you go through, from humulus, you have cumulus humulus, which is basically your fair weather cumulus clouds, all the way down to Spisatus, which I hadn't heard of before this, but they're all classified according to the features they look at. Lenticularis, wave clouds, you very frequently see those over mountains. You'll see pictures from the Rocky Mountains or the Cascades out west, or Sierra Nevadas. We'll see these very smooth and almost flying saucer-shaped clouds over the mountains. Those are lenticular clouds, and they're produced by the winds moving over the mountains. Then we have varieties. We actually have vertebrates, radianus, and all of them describe a feature. This is translucent clouds, opaque clouds, and we're going to see examples of these as we go through. And over here, it lists some of the cloud types. SC is stratoQ, altoQ, altostratus, cirrus, and cirrostratus. And we'll get into that a little bit. And then accessory clouds, and we will talk about a couple of these. Panis clouds, Pileus clouds, which you can easily observe around here during the spring and summer, during the thunderstorm season, and velum clouds. And there's other accessory clouds as well. Supplementary cloud features, Arcus clouds, those you'll see here, we'll talk about those. Mammatus, obviously precipitation comes out of the clouds, and that can look like something else, and we'll see some examples. Virga, which is precipitation falling from the cloud, but it evaporates before it actually reaches the ground. So you get this thin, usually translucent shield or gray curtain of what looks like cloud, but it's actually precipitation falling out. Then we have funnel clouds, and last but not least is contrails, which are artificially produced by aircraft, but they actually are a cloud classification. So we get into high clouds. Now, cirrus clouds are generally performed of ice crystals, and they're generally anywhere from 18 to probably in excess of 50,000 feet. I've actually been flying at 37,000 feet, which is pretty high for clouds, and actually had an overcast of cirrus clouds, which doesn't happen very often. Usually at 37,000 feet, you're above everything, or you can be flying it. So they can get up very high. The wispy appearance is due to, generally, because they're high up, they're subject to stronger winds, so they can tend to stretched and torn apart. And then here's an example of cirrocumulus, and the cirrus, the cumulo part of it is fairly minor, but you can see little puffs of cloud here, which give it that rounded shape. But all this is ice crystals falling out of the cloud. And there isn't much cloud there, but the ice crystals are actually falling out.
Steve?
Mm-hmm.
between the white and the blue, what's the difference in the water content?
That's a good question. It's not, I would say this probably isn't quite saturated. It's close to it, but at those temperatures, comparably, there's less water vapor in those clouds than clouds 10,000 feet low.
Sure.
So, offhand, it would be hard to say, but it would be interesting to run a sounding up through that. But it typically would, at this stage, you probably have a fairly deep layer of moisture in the clouds. So the relative humidity in general through that layer would be fairly high. But between the exact white and the blue,
I just never understood.
Yeah.
Professional, tell me why it's not either cloudy or clear.
Yeah. Well, and that's partly due to the upward and downward motion of the clouds. Typically, where you see the clear areas is where air is descending. Okay. And descending air tends to warm. All things being equal, if air comes from 10,000 to surface, it will warm several degrees. I'd have to calculate exactly how many. And if you take air from the surface and just raise it to 10,000 feet, it will cool. So, and on clear days where we get the flat cumulus clouds, we call it the fair weather Q. Usually in between those clouds, air is descending, but where underneath the clouds is where the air is rising. That's why you're getting the cloud. Probably in those cases, usually due to thermals, just the ground heating up, and you get little thermals bubbling up. But generally, where the sky is clear like this, we'll see some other examples is where air is descending. Because the air is going up, it just doesn't keep going up and stop. It eventually comes down and it usually rolls over. Altocumulus clouds, which we'll get to here shortly, is a good example of that. So here's your more typical cirrocumulus, I think. And these were actually taken, this was actually taken here in this part of Illinois. You get the rose, and this is due to the winds in the upper atmosphere, producing upward and downward motion between those rows. So where you see the clouds is where the air tends to rise. And these here are lower, probably, these are closer to 20,000 feet, while these are probably closer to 15,000 feet. Okay? And this is often called a mackerel sky, because it looks like a fishbone. And usually these come, you'll see these post-cold front, fair weather, is when we see the cirrus clouds, especially at the tail end of a storm system moving out. The clouds will get higher and higher. You'll see the cirrus wisp out, and then you'll have clear skies maybe for a day, and then the next round of cirrus clouds comes in as the next system comes in. Cirrostratus clouds are fairly thin, tend to be milky. They can cover a large portion of the sky. This is not a particularly large portion, but you can see it's pretty continuous and thick, but you can still see undulations in the cloud where there's a little more rising motion and descending motion going on. More typically, we can see something like this where you see the moon or the sun through the cloud layer. On daytime, you'll actually probably see shadows with that, but this typically form if you have a large weather system headed your way. You get a very large area of rising air. It's not like a thunderstorm. It's over maybe 100 miles or more, and then broad area lift just rises up, and eventually you get that cloud layer when that air finally saturates and forms clouds. Middle clouds are, I think, one of the more interesting ones. They occur in the mid-levels of the atmosphere, roughly, as it says, they're from 6,500 to 18,000 feet. That's quite a range, but typically around 10 to 12 is where I think most of them tend to occur around here. They can appear in streets or look like waves. Common in advance of a warm front. There's a lot of different classifications of them. This is actually a wintertime photograph. This is actually taken in the morning, but you can see again, there's very distinctive streets in here where the air is rising and falling in between the cloud bands. So this is why we get, people think, well, the clouds come in with a cold front and the storms and everything, but anything that causes rising air can form clouds. And When the warm air starts advancing back northward, it's what's moving, and as that warm air slides up over the cold air surface here, the warm air is moving like this, and this is receding, maybe not quite as fast, so you get that mixing in here, and you get the warm air condensing and forming clouds. And typically out of a warm front is when we can get thunderstorms, but we can get a lot of stratiform rain. In the winter, those are those crummy, dreary days. A warm front will be south, we're still 35 degrees and it's raining. And it just rains all day, and the clouds are just a leaden sky. But that's typically because we got that warm air, and we call that overrunning, because the warm air is overrunning the cold air, and that's producing clouds and usually precipitation. And the stronger the system, the more intense the precipitation, and the further north it spreads, north of the warm boundary. But as I said, in the wintertime, early spring and late fall, you can get a couple of days of rain out of one of these systems, depending on how fast they're moving. This is a particularly telltale cloud, the altocumulus castellatus. And the castellatus refers to the turret, the towers. I've been watching for an opportunity to get a really good image of this, because I've seen examples, I just haven't had a camera. But what you're getting is that mid-level cloud, you're getting more vertical development. You see small towers and small turrets. They're not huge developments like thunderstorms, but definitely you can see the towers. If you see those in the morning, late morning, typically early afternoon, that's likely to be a pretty good severe weather day. Because the atmosphere, what that's telling you is that there's rising air in the mid-levels of the atmosphere already. And it usually doesn't take much for the atmosphere, just something to set it off and start getting thunderstorms going. So if you see this type of what we call convective look to the clouds, where there's little turrets or puffs, and probably in this image you probably see something more vertical. It's hard to get 3D on some of this. But that's usually a good telltale sign that you're in for a potentially thunderstorm day, at the very least, and maybe severe weather day, especially if it's going by mid to late morning. Here's a more interesting altocumulus. You can see this. It's a little bit washed out on the screen, but you can definitely see the waves in the clouds there. This is taken at sunset in the winter, so you get a brilliant red, orange glow behind it. A spectacular photo. But those are definitely altocumulus clouds. But because of the strong winds in the atmosphere, you're seeing the undulating feature of that particular cloud. As I mentioned, that getting ahead of myself, the altocumulus castellatus are usually a good sign that you're in for some rounds of thunderstorms. Now the more sometimes boring, but usually interesting alto clouds or altostratus. Here's a better example, at least in terms of definition and resolution, of altostratus undulatus, where you know that it's very windy up there. If you're up there flying, that's one turbulent day up in the air, okay? Especially if you're passing through this layer, because you got strong mid-level winds which are causing those waves. It's similar as if you were watching the water roll back on itself. But as the air moves along, you get rolls in the air, turbulence, or you watch off the tip of an airplane wing where the air rolls. Something like that can happen here, and you see these undulations in the clouds. Typically, these are sort of thicker clouds, and they tend to be dense, and usually don't yield any precipitation at this stage. Here's another example. You can see sun, like we used to say in forecasting, sun dumbly visible. It's actually commented sun dimly visible, which means you can see the disk of the sun, but basically the sky is overcast. And this particular one, you can also see some lower level fractured clouds in the image as well. The low clouds are the ones that tend to be, well, they can be interesting, but generally up to 6,500 feet. We had a stratocu, which is could be indicative of fair weather. The stratus, which generally is that leaden sky. There's no feature to it. looks completely gray, completely flat. And then, but the other sums, like fair weather cumulus, are often included in this category. Fog, when on the ground, is a type of cloud, especially if it's a widespread fog, not necessarily what we call radiation fog. Especially now in the spring, you will see days where you'll go by a field and there'll be fog hanging over that field. You'll go to the next field as you're driving into town and it is clear. That's a little different, but widespread fog generally forms as a cloud. Stratus clouds, as I said, are generally featureless. That leaden gray you see, generally they are precipitation producers. If it's heavier precipitation, there's usually another layer or two of clouds above it that are actually raining out. They tend to produce drizzle or in winter snow flurries. And then sometimes you will actually see these clouds racing underneath a lot higher cloud depth. I mean, they will look like they're just screaming along at the lower level, winds are high, and you can see them moving. But typically, there's not much feature to them. You just look up and you don't see anything except gray. Stratocu, this is where we get into more closer to the fair weather types. Large, rounded, dark masses, all these little spaces, which are very small here, is where the air tends to descend. But almost every one of these little pockets is just thermals going up in the atmosphere. So, in fact, sailplane enthusiasts look for cumulus clouds forming to pick up thermals when they're flying, because it's a good sign that air is rising. They're lower and larger than the altocu, and they are formed by convection, i.e. rising air. And often it's usually very cold waft, and there's usually a layer above that's stable, so these clouds usually don't have much vertical extent. Sometimes they do, and you'll get a little bit of precipitation, they get a few drops of rain out of them or a few snow flurries, but in general they don't produce precipitation. Now these are stratocu that form after, and it's in a cold air that was taken during the winter, and you can almost see over the top of them. They're not very thick, maybe 1,000 feet, if that. So they're very fractured. They're very. You can actually see them come and go. If the atmosphere is particularly active, you can watch a cloud and it'll just sort of fade away, and another one will take its place if they're moving along. Typically, when you notice they increase, early afternoon as we get toward the heating of the day. We see this a lot in the spring after a cold air outbreak. You'll wake up in the morning, the sun's out, not a cloud in the sky. 11 o'clock, all of a sudden it's cloudy. That's because the air has been basically unstable, and as soon as we heat the air at the bottom, that air starts to rise and it forms a cloud layer. And then at sunset, what happens? Well, the air stops rising because they're cooling off and the clouds dissipate. And until that unstable layer of air moves out, maybe the next day or so, you'll continue to have that cycle of clouds in the day and then dissipating in the evening. Now, stratocu are very common over the ocean, especially the Pacific, where you have very cold water underneath, and you get warm air, or moist air flowing over it. The marine layer, which is off the coast of California generally, is most of the time a fog or stratocu layer that moves in and out depending on the heating of the land and difference in heating of the land and the ocean. But typically, huge areas of the ocean, especially the Pacific, where the water is pretty cold, are very common areas for stratocumulus clouds. Now we get into vertical clouds. The cumulus clouds, or the cumulonimbus clouds, which give us all our excitement during the spring and summer season. And as I said earlier, they can get up to 70, 75,000 feet in extreme cases. More typically, your severest thunderstorms will be 55 to 65,000 feet. And that's typically how we look at it. Oh, that one's up to 65,000. You almost have to look at radar to know that's going. And the reason for that is to get a cloud that high, you need a very strong vertical motion. You need air really, really screaming upward to get that kind of vertical development. So our fair weather cube, called fair weather cube, not different than the straddle cube. In fact, often it's one and the same, but not much vertical extent. Their bases are generally larger than their vertical extent, and those are the type that will form in close to the heating of the day and then dissipate late afternoon toward sunset. And just typically, there's moisture in the air, you've got some heating and some rising, and that's all it really means. They're fair weather cube, usually on the east side of a high pressure system as it's moving over us. Now, this is a little bit hard to see. It's an evening shot. This is cumulus congestus, and this is where you're starting to see shower and thunderstorm development. And here's the cloud here, backlit by the sun a little bit. You can see the cauliflower look to it. That means that there's air rising in that particular cloud in one or more updrafts. And we often call these towering cube, which lets us know, which is sort of the signal that air is rising pretty good and likely to be a thunderstorm. Here's another view of some cumulus congestus. This is a sort of a busy one. There are a lot of cloud layers in this particular photograph. You have some lower clouds here, a little straddle cube in here, and you have the nice developing towers here. But then you also have some higher clouds, probably almost an alto cube, a thick layer of alto cube that's more or less blocking out the sun, giving everything that grayish cast to it, because there isn't much sunlight getting in, except near the top here where the clouds are a little bit thinner, you're getting some light. So, but you can see here, you got an updraft going here, there's a tower here, there's another one here, and I'm sure there's others in that photo, there's probably one here, that were hidden by the lower clouds. But this happened to open up a window where you can see the cumulus congestus really well. Then we have cumulonimbus, also called thunderhead, also for short CD. That's our shorthand slang for thunderstorms is CDs. They grow vertically. Again, you have to have strong updrafts to get storms up to 60, 65,000 feet. If you've ever taken a storm spotting class, you'll learn there's different types of thunderstorms. There's multi-cell clusters, there's individual supercells. There's, every once in a while we get a nice calm summer day where you have one thunderstorm popping up in the middle of nowhere, and it's the only one in 200 miles. They get an isolated one like that. But generally, there's several different flavors of them. But you can definitely see, this is particularly where one strong updraft is, and this is where the main storm is, but you can already see another one starting to form here. And probably what happened with this one is this one grew and matured and then died out. In the meantime, this one was growing and becoming a mature thunderstorm. And then when we get really strong storms that tend to be in their own environment by themselves, or maybe with groups of others, we call them supercells. They tend to have their own circulation. And if you ever watch time lapse or actually get to see a good one in the field, you could actually see the whole storm rotating. And that is what we call a mesocyclone. And those are the ones that produce the tornadoes. And the stronger ones produce the really big damaging tornadoes. In fact, last November 17th, it was supercells that hit Washington, Gifford here in Champaign County. You definitely see the rotation on radar. Because there was a lot of precipitation associated with those, you can't visually see it in the field, but you can certainly see the rotation on radar. And they're generally separate from the rest of the storms. And when the storms start forming into lines and clustering together, they tend to weaken each other. You don't get quite the damaging tornadoes that you do when they have their own environment. So we have different stages of storm development. This is the pre-cumulonimbus stage, and this is called cumulonimbus pallus. And it's puffy rounded top, and typically, after you start seeing this maybe early afternoon, and if you start seeing this, something's going to happen. Someone's going to get showers at least, or thunderstorms at worst, in the next couple of hours. So the next stage is when it starts getting more cirrus type clouds near the top. And you can see already here, this is starting to flatten out. which means it's probably reaching, it's getting sheared off by the upper level winds. And you're getting the fibrous, wispy tops. You can see some cirrus up here, which may or may not be associated with that particular cell. But you can definitely tell that that's starting to flatten off. And the winds aloft are starting to shear that off. And that's called capillatus. Now this is Cumulonimbus incus. This is a classic anvil top. And you'll see, I mean, this was actually taken, I took that 2 years ago from the eastern part, not far from where I live out near Homer Lake, but that storm was actually close to Indianapolis. And I took that photo from near Route 49 here in Champaign. But the neat thing is the sky was a fairly dry day here, so that you had good visibility. There wasn't a lot of haze. It's a problem with observing storms and clouds around here is because of the high humidity generally during the summer and spring, lots of cloud features are masked by haze. And it makes it difficult. That's why all these spectacular shots you see out west in Oklahoma, Kansas, of the storms, their air that's lower levels there are usually so dry that a lot of those storms, it takes a while before they actually start to drop rain. Actually, they drop tornadoes before some rain sometimes. But the air is so dry underneath them that you get great visibility. Here it's a little bit different. We got the Gulf of Mexico sitting to our south. Frequently we get a lot of humid air here. And, you know, but that's 100 miles from where I was taking the photo. And that's pretty unusual. You get that kind of visibility and that kind of resolution. But what happens here is this is the mature thunderstorm. The top is definitely flattened out. You can see the thin, wispy edges here, well defined. And here's already other updrafts, other storms beginning to form behind it. So, and I think there's a couple more visible, not quite as spectacular as that. But typically you can see those a long distance. And I think that one was close to 55,000 feet when I took that photo. So the storms actually grow into the tropopause, and every once in a while you'll get a really strong storm that actually the updraft blows through that top. It's called an overshooting top, and those are the ones that typically produce the most damage because you're getting such a strong updraft. It's actually blowing through that shear level in the tropopause, and what goes up usually comes down, and that air that goes up comes down. That's what gives you your strong thunderstorm winds, your downdrafts, and can cause rotation as it comes down, forms the tornadoes. And here's your classic supercell, not taken here in Illinois. This is one of the Oklahoma storms, but you can see all the different features of this. You get the striations along here. It's flattened out. It's very thick. It's huge. Incredible updraft in here. I have no idea what the diameter was down here. And probably if you had watched, if they'd taken a movie of that and we were showing it on time lapse, you would see the whole thing, that whole storm rotating around as a mesocyclone. And because they are a self-contained circulation, it's not uncommon for them, you know, let's say, typically we say storms are moving to the northeast at 50 miles an hour. Occasionally you'll see one of these storms take a right turn off its path. The one that hit, it wasn't more, that was the second one, Enid, Oklahoma? It was the one that hit Oklahoma the second time last year, was the storm chaser got killed. But it was near Oklahoma City. That storm took a sharp left turn, and nobody was ready for it. And that's partly why that one storm chaser, Tim Samaras, who was not just a storm chaser, he was a researcher, was killed because unexpectedly caught him. So these are going to be very dangerous storms, and they're sometimes very tough to forecast. It's gotten now to the point where meteorologists can tell on radar what that storm's going to do. There are some signals they can say that this thing's going to start turning right or start turning left. But because they are sort of self-contained, they can be a lot more dangerous than other particular thunderstorms. And they'll get obviously strong downbursts, which can produce more damage than any kind of tornado, partly because it's also more widespread. This is where you get the golf ball, the softball, the grapefruit-sized hail. Again, because strong updrafts carry those hailstones well up into the storm until they get so heavy that gravity takes over and they come down. Usually when they come down at that point, they're huge. I mean, 4 inches in diameter. So they can be really big. And these are really impressive storms. So some accessory and miscellaneous clouds. A lot of these are associated with the cumulonimbus clouds. We have Pileus, Amatus, which you've probably heard of. If nothing else, probably one of the TV meteorologists talking about it. A wall cloud, which is a very common telltale sign of potential tornado. You've probably heard that before. A beaver tail, probably not one you've heard before. A shelf cloud or roll cloud. We've seen those here, obviously, and you probably have heard of those. And tornado, which everybody's heard of. So Pileus is a cap cloud, and it's a very thin, sometimes lens-like cap over the top of a towering thunderstorm. This one looks like it's parked right on it, but sometimes there's actually some separation between the top of the cloud and this cap, and it almost looks like a lenticular cloud over a mountain, except they tend to form over the tops of the thunderstorm updrafts. They are ice crystals. They're probably, depending on how high the thunderstorm, 30, 40, 50,000 feet. And they don't last a long time, partly because the updraft doesn't always last a long time. So they'll only last as long as the updraft is that strong. And most thunderstorms cycle through updrafts. So, but it's an interesting feature to see. And if you see that over a thunderstorm, you know that that's probably a pretty good thunderstorm going on the ground underneath it. Amatus clouds, how many have seen Amatus clouds here? It'd be hard pressed if you hadn't gone out after a thunderstorm sometimes to see them. And you don't have to actually have rain near you. If it's a thunderstorm in proximity, you can see these. But they resemble pouches on the underside of the anvil, typically. And they're formed by descending air. The air has gone up into the thunderstorm. As it spreads out and cools, it starts to descend. And as that descends through that anvil, it forms little pockets of descending air, which punch out these little pouches of cloud altitude they're at. That's a really good photo. Not my photo, unfortunately, but that's pretty impressive example. So, but I think if you look this year, in this thunderstorm season, especially after a thunderstorm's gone high, and you're seeing some sunshine or it's starting to clear a little bit, you look underneath that anvil, you'll probably at some point see Amatus clouds this year. When I was growing up, the thing was, if you've got Amatus clouds, a severe thunderstorm, and you're going to have tornadoes. Well, that may or may not be the case, because to get those kinds of rising air and that descending air, you usually get a very strong updraft. So probably in most cases it is a strong thunderstorm. Whether it's severe or not is hard to say, but it's usually a good indication of strong updrafts in a thunderstorm. Now we get into more storm-specific features. We got a wall cloud and beaver tail. These are indicative of a storm updraft. And anybody here been through storm spotter training, other than myself and Jesse? Okay. These are features that they point out, and that's what we look for in storm spotting, for example. And these were, the wall cloud was visible in Washington and also in Gifford in November. But they're indicative of very strong updrafts. And typically, this is where produced with a supercell / mesocyclone. So this wall here indicates the base of the updraft, because what's happening is you're getting warm air coming in there, warm moist air, and it's condensing beneath the cloud, and it's forming that wall cloud.
So that's the wall cloud that's hanging down?
This is the wall cloud right here. Well, I got a better photo of it coming up here. And then the beaver tail, which is this little appendage here, is showing you where the air is coming from. Points toward the source of the warm air. So there's a better example of it. Again, around here, we don't always get them that clear, depending on the surrounding atmosphere. But you can definitely see it looks like a core. It's a wall cloud. What we watch for is rotation in that. If that whole wall cloud is rotating, and I don't mean spinning like a top, it can be rotating slowly. That's usually a sign that we have rotation in the storm, and we need to be watching for frontal clouds or tornadoes. And then the beaver tail you can see there. And what happens is you get warm air coming in and then up into the storm. So we know, you see that beaver tail, we know there is strong inflow coming into that storm. Now, in some areas like out west, where you get the strong inflows, I mean, inflow can be as much as 30 to 45. You could be standing there in sunshine, 30 to 40 mile an hour winds. That's what's flowing into the storm, and which produces the supercells. Here we don't get typically those kind of inflows, but that's how that works. And because that warm, moist air is being pushed up into the storm right there, that's the updraft. And then back here, where it's a little clearer, is where we're getting descending air.
Is that the comma they always point out?
No, don't have any examples of that. But the hook echo, you mean?
Yeah, I see that.
Actually, if a tornado forms and the circulation is strong enough, that would be the location of where the hook is.
Okay.
Because you're getting, what the hook is showing, basically, is the rotating air. And, or rotating air, rain particles in the air. What is detecting is the raindrops. So that hook echo will be, the center of that hook will be where that tornado is, or where that fault cloud is. These can be really scary looking clouds in the spring and summer. And people think, I mean, they're always worse than tornadoes because they look huge, they're bearing down on you, they're dark, they're ugly, they can be green, lightning and thunder behind it, but they're called shelf clouds. And typically, they do mark some strong winds, and the strongest winds will be right behind that cloud. But what's happening is air is coming in, as the winds are pushing the air ahead of it. This is, say there's a line of thunderstorms there, and that air is being forced up and over, and you're getting air coming in like this, and it's being forced up, it's condensing into that shelf cloud. And because it's moving forward here, you're getting that angled look to it. So it causes condensation. You might see a lot of turbulence. You might see a lot of vertical, horizontal rolling, the cloud rolling in on itself. You usually won't see much vertical rotation. You hope you don't, because that usually means something might spin up. But typically, you can see vertical rolling. The clouds beneath you can be very turbulent, up and down. You see fraction. You see strato-Q coming out and dissipating. I mean, it really looks ugly and active and dangerous. Dangerous it can be, because typically there's strong winds behind it. There can be 70 mile an hour wind gusts behind this easily. But in lots of cases, they look worse than they are. And right after this, you'll get the strong wind gusts, and then a few seconds after that, the torrential rain. And then you're pretty much done. You might rain a long time. So that's what a shelf cloud looks like. And usually, again, it usually indicates a fairly strong system coming through. This happened, I think, 2 years ago. A colleague at work took this photo out near 57. It happened in the morning. It happened about between 7 and 8 o'clock in the morning. And a strong line of thunderstorms came through, but I had never seen the sky look so confused and chaotic as it was that morning. I mean, these weren't necessarily moving, but you could really see a lot of different patterns in those clouds. The winds up there must have just been nuts. And not just being speed, it went direction and up and down. It wasn't your classic shelf cloud where it was one smooth thing that came through. It was this very odd-looking, undulating cloud with all this texture in it. And it just was very strange. But it came through here, it came through Champaign-Urbana, sometime around 7:30 in the morning, which is why he was on his way to work and took that shot. And here you can actually see some rain falling here. We'll talk about that. But that was really an interesting system, and I'd never seen anything quite like that. A roll cloud, very similar to a shelf cloud. It also looks ominous and associated with thunderstorms. It's usually out ahead of the line of thunderstorms, and it's produced much the same way. You got air flowing out, it rolls up and around, condenses the air, you get this roll cloud. It sometimes will have a horizontal roll to it, but it's usually very smooth. And right behind it, you'll get, or right with it, you'll get the strong winds, and right behind it, you'll get usually very heavy rain. You can see the rain. You see the rain back here. You see the streaks of rain coming down. So you see one of those coming, and you know that you're going to get windy. Your temperature's going to drop probably around 10 degrees or more, and it's going to rain like crazy for a couple of minutes at least. But it's usually not attached to the thunderstorms. It's out ahead of them as that cold air rushes out ahead. The shelf cloud tends to be more attached to the thunderstorm itself. But this one, the wind gusts get well ahead of the thunderstorms. You can tend to see the shelf clouds, or the scroll cloud rather. Okay, is that a funnel cloud or a tornado? Anybody know the difference? Tornado. Anybody know the difference between a funnel cloud and a tornado?
I got what it
Touchdown.
touched the ground.
Right, a tornado's on the ground. A funnel cloud is a tornado that hasn't touched the ground. That's the way I like to call it. And the reason we know this is on the ground is you can't really see the condensation funnel. You can't really see it much past here, but if you look toward the ground, you definitely see dust and debris, which means it's on the ground. And eventually that whole thing will probably fill in, and you'll have a small, probably EF0, EF1 tornado going on there. That's a pretty high base too, but this part here is the wall cloud, and you've got the funnel coming down.
Did you take that picture?
No, I didn't.
So what about,
I've only, to be honest, really, I only saw my first tornado here, ever, here, about 5 years ago.
Yeah, I've never seen
And I happened to be out at Willard Airport one afternoon. I was leaving to go on a trip, and I was sitting there and it was a very odd situation. We had a front just south of here. It was pouring rain in southern Champaign County over to Douglas County and Piatt County. And actually, you could actually see bright sky to the west a little bit. And it was lightly raining here. And I saw two guys. I was sitting on the floor on my computer, and I saw one of the UI policemen and one of the security guys staring out the window out over the airport. And I thought, what the heck are they so looking at so intently? And I got up and looked, and there on the other side of the airport was a tornado. It wasn't a very big one, and it wasn't moving very fast. In fact, I don't think it even made it to Duncan Road, but it was sitting there. Of course, they got us all downstairs and evacuated, the upstairs to the terminal. They dissipated. It was a weak thing that was associated with just the circulation on this front. That was the first one I ever saw. And it was sort of exciting, but it wasn't much of a tornado. But and I did see another good fall cloud about a year later as I came out of Walmart in Savoy, and right smack in front of me was this long funnel coming out. Well, I actually quote chased that. It didn't last very long, and it was more of a cold air funnel. There was a thunderstorm around, but it wasn't more of a cold air funnel type, which we'll talk about. But I've never really chased. I haven't had much of an inkling to do that, although I ought to probably put it on my bucket list. Contrails. Obviously, we know contrails are from exhausted jet aircraft. One of the more interesting contrail studies ever done was done on the days after 9/11.
Yeah.
Every aircraft in the U.S. was grounded, and researchers had an opportunity of a lifetime to study the weather without those contrails in the way, or the effects of contrails. They actually had it's hard to do comparison studies of weather with contrails and without, because they're very often not without. So this gave them a great opportunity to do some research with that. But that you typically see, you don't see them all the time, and atmospheric conditions actually dictate that, obviously. But one of the things, you may have heard of Stan Shagnon. He used to be a state climatologist here, very famous climate researcher here at the Water Survey. One of the first things, that he found out about contrails is you're typically going to see an increase in contrails in the sky ahead of a warm air coming in, warm front. So if you see a couple of days of cool air and all of a sudden contrails start filling the sky, it's likely to warm up, because the warm air is already coming in at upper levels, which is causing those contrails to form. And eventually that warm air down at the surface will get there. So it's usually a good indicator of stuff like that. But it sort of depends on where you are. This could be up near Chicago, where air traffic, or northern Midwest where air traffic is really thick. Here it's not always, but you definitely can see contrails better on some days than others. Some days you see contrails and they basically dissipate. I don't know what the distance is, but not long after the plane goes by, you'll see the contrail disappearing by it. Other days, the plane will go by and the contrail will still be there hours later, depending on what's going on. So these often spread out, like in this case, they can spread out and form actually a thin cirrostratus layer. Actually causes some diminishing of sunlight, but they're now a permanent feature of our sky as long as we get jet aircraft around. Fractus clouds. Talked a little bit about them. You see those sometimes with those roll clouds or shelf clouds. You'll see just little wisps of clouds or clumps of clouds that tend to form and dissipate as the air rises ahead of the turbulent system. They can exist where you have strong airflow at the surface. You might have a nice stratus layer, but then you get some even more moist air and it gets a little bit cooler and you'll see these fractus clouds come down. But typically they tend to occur in and around thunderstorms because you're getting rising air, which causes those parcels of air to condense and form little cloud fragments. And this one here, this is a fractus cloud. Photo was taken just east of Urbana, near Mayview, I guess. And that was actually recorded as a funnel cloud tornado. And actually I took that because I was asked about to check that report. And the reason we knew it wasn't was there was no rotation to it. It remarkably held together. I mean, they don't usually get very persistent. They'll tend to form and dissipate or change shape or rise up into the cloud or disconnect from the cloud. But that one remained fairly constant for, 10 minutes or so. But there was no rotation. And there was no rotation with it. A lot of heavy rain behind it, but no rotation. And that heavy rain was causing cool air to flow out ahead of it, causing rising air, which helped form that particular cloud, and others like it. And they are often mistaken for funnel clouds. So this is why star spotters are told to look for rotation, because it's very hard to tell sometimes, unless you can actually see something spinning, whether or not that's a funnel cloud. Virga, we looked at this particular photo earlier, but they can form from high cirrocumulus, but actually more often than not, you'll see it from lower clouds. And you can see it from thunderstorms, especially if the lower levels are fairly dry, so you have good visibility. If you have a lot of humidity, a lot of haze, you're probably going to have more because anything falling will actually reach the ground. But in very dry climates, you see this all the time. You see rain, curtains of rain coming down on high base clouds in the west. New Mexico, Arizona, Colorado, that never reaches the ground, probably never gets past 10,000 feet, but you just see the curtains coming down. There's an example. I don't know what altitude that is, but you can definitely see that there's the rain curtain there, and then towards the bottom, everything's evaporating, so it never reaches the ground. And that's called virga. So it does indicate that there's active precipitation going on. The clouds are trying to produce it, and usually just means that the lower levels are so dry that you won't get the rain. Today, we had a line of showers approaching here late this afternoon. I don't know if anybody got any where you were. Tend to break up before they got to Champaign County. But, the temperature was close to 70 this afternoon. But the dew point, the indicator of how much moisture in the air, was 35 degrees. That's extremely dry. We don't look at relative humidity because relative humidity isn't relative. We look at the dew point, which tells us how moist the air is, and the 35-degree dew point in the spring is extremely low. We get thunderstorms when the dew point is 55, 60, and that type of thing. Then you're going to get thunderstorms. But though, as those showers moved into this very dry air over us, they basically evaporated. It was just not enough to keep them going because the air was so dry. And I imagine there was some virga to be seen if you happen to be around some of the showers. Like I said, they went north and south in Champaign County this afternoon, which seems to happen a lot. So here's a rain shaft. which is nothing more than it looks like a burger, but this is actually reaching the ground. And this is, the updraft is probably somewhere over here, but this is rainfall falling. I don't think this time there was any thunder with it, but I happened to be coming home from work last summer and took this photo. It was in July. And we hadn't had rain in several days. In fact, I don't think there was even a forecast for rain that day. But I noticed going home, and I was going home early that day around 3 or something, that the sky was very convective. There was a lot of buildups there, and I thought, I thought we're not supposed to have much in the way of rain. And then as I got further east towards Urbana, I started noticing this particular shower. And this is taken south of St. Joe, and that's looking northwest, and I have to see this rain shadow. And it was pretty spectacular. Again, because of conditions around us very often, you won't see that because of the haze and fog. But because the air was generally dry, and this particular shower managed to be the only one within 200 miles that day. I checked radar when I got home. This is what it looked like on radar. Now, I am where the red triangle is. That's where I took the photo from. And so I'm looking northwest across 150 and I-74. So this is east of 57 and north of 74. And let's see, we got mile sections there. It's maybe 5 to 6 miles in diameter on the long axis there. And it basically sat there for about 45 minutes. It didn't move. There was not much movement in the atmosphere. There was not much upper level winds. So this thing basically went up and sat there, rained itself out, and eventually that updraft stops or gets cut off, and the thing dies out. And it sat there for, like I said, about 45 minutes before it finally rained itself out. Now, don't know how much rain fell in there because we don't have any weather observations or rainfall observers in that particular area. Hint, hint. But radar estimates were about a ½ inch to 2 inches. So that was sort of in a very dry period, right around pollination time for the corn. So some farmer was really lucky. Or maybe a few farmers were really lucky in that particular day because that thing really poured out. Well, I don't know. I was probably seeing this particular, probably seeing this end of it where it was really raining out here, where the heavier rain is. Obviously couldn't see past that. But that's where that photo, where that storm was at relative to me. And this line here actually shows which way the radar thought it was moving, which would be toward the southeast, but it basically wasn't moving at all. So that was sort of an interesting look at what you see from the ground and what you see on radar from the same particular storm.
So what's the source of that image?
It's actually a radar program called GR Level 3. Anybody can have it. It runs on PCs. Windows machines, I should say. Yeah, if you want to know more about it, I'll tell you later. But it's a nice little image, and you can put the, in this particular case, it had the satellite images on it, so you can see where things were. So, very interesting aspect of a particular rain shaft, as you can see. And then cold air funnels. How many have seen the cold air funnel? Yeah, they're not uncommon around here. Typically, you can see them in the spring and fall. Once in a while, we get a really strong cold frontal passage in the summertime, the day or two afterwards, especially if the cold air doesn't sweep through here, maybe stalled out just south the front. You can see cold air funnels. But they develop a shallow cold air mass, but usually, like I said, typically if it stalls out south of here, which means the air is still rather shallow. We don't really get into the deep cold air. And usually the winds aloft are fairly strong, so you get what's called wind shear, which is either a change in direction with height. If the winds are at the surface are out of the northwest, but they're still out of the southwest aloft, that causes rotation. Or if the wind speeds are different as you go up, that causes rotation. They don't typically reach the ground. Actually, I don't think I've ever seen one rotating. It does rotate, obviously, it forms a funnel, but they're usually high enough where you don't see the rotation. They can reach the ground once in a while, and they might produce some minor damage. Probably, I mean, a strong dust devil can do that. Anybody see dust devils during the winter here, or I mean the summer? I mean, if one of those gets going really good, you can get a little bit of damage depending on the winds. But more often than not, they're a curiosity and they're neat to see. Now the weather service will actually put out special weather statements saying, today is a good day for cold air funnels because we don't want a zillion people calling in the tornado. Because they know what conditions are good for cold air funnels and they know when to expect them. The good thing about the special weather statements and mentioning that is you can keep an eye out for them and see some really neat cold air funnels. And they can be short, stubby things that might be only sticking this far out of the cloud, or they can be something long like this, which extends 2/3 of the way to the ground. But they typically are high-based clouds, usually alto stratus or alto cumulus, and probably up anywhere from 8,000 to 12,000 feet as the cloud base, which is pretty high. But they are interesting, and if you live here long enough, you're likely going to see them. Now, some cloud information sources. If you really like watching clouds and seeing what's on, there's actually a Cloud Appreciation Society. And seriously, these guys are serious. They've actually come up, I think in this last year, someone actually discovered a new cloud. And they take their clouds and cloud classification seriously. I can show you a web page real quick. But there's a lot of really good photography on this website. And it's Cloud Lovers Unite. There's usually photos of the week. And this is based, I think, in the UK, of course. I mean, Cloud of the Month Club. Cloud of the Month. So, the Cloud of the Month for March 2014. Nice cumulonimbus cloud. So, there's, I mean, you could waste a lot of time. It's very neat. And you can be a member, and I am not. I don't need another hobby right now. But they do have some really neat photographs, and it is a very cool website. So that's one source, and then there is. Go down the whole thing.
Go back down.
Yeah, we're gonna go down here. There is another. There used to be a group called For Spacious Skies. Yeah, and they were really active 10, 15 years ago. That they had postcards, and I actually was a member of that for a while. They seem to have sort of died off a little bit, but it's another source. And then the Royal Meteorological Society in Great Britain, has a really nice website for clouds called Metlink. So the Brits really get into this stuff. And I think the Cloud Appreciation Society is based in England, and so is obviously RMS. So there are some sources there. You can get some sort of decent cloud charts from NOAA, but frankly, I've never been too impressed by them. With photography these days, and digital photography and the web, there's a lot of cool stuff on the web just looking at clouds. But the Cloud Appreciation Society is really one of the better websites for that. So if you're interested, I would suggest you wander over there. Now, I said earlier that I had to, I'm Illinois coordinator for the Community Collaborative Rain Hail and Snow Network, so I'm sorry, I'm hijacking this for another 2 or 3 minutes to talk to you a little bit about COBRA-ROS. And it is, it's our website, but it is one of the largest citizen scientist programs in the country now. We are the largest provider. We provide the most precipitation observations of anyone in the country, more than the National Weather Service, more than any other organization. This group of volunteers provides the bulk of precipitation observations in the U.S. And if you're interested in the weather, whether the clouds or what falls out of clouds, or you're a master gardener, you're worried about how much rain has fallen, or a master naturalist, and you're also worried about how much rain has fallen, or not fallen in that case, we are always looking for observers. And anybody in here? I know Jesse is. You're an observer? Okay. What's your station?
CP 58.
Okay. Anybody else? So we have 2 in here, 3 actually, because I am too. But we always need observers. And you might look at a map and say, well, you got plenty of guys in there in Champaign or wherever. But we always, more observations the better. This is an example of an Illinois map. Every dot in there is a precipitation observation that's been reported. This is an Illinois map, which is why you see the counties on this one, and you don't see the counties on Indiana, Missouri, and Iowa. But you can see where the concentration is, largely up north, obviously population centers. And we do have a pretty good group of observers here in Champaign County. This is from 3 days ago, March 28th. We didn't have a whole lot of rain, but you see we had about a 1/4 inch. But you also can see where we have most of the people concentrated. Mahomet, Champaign-Urbana, we got a few out in the south. That's me, up eastern part of the county. We got 1 or 2 up north, but we really need some more up the northeast and the southwest part of the county. You know, if you're out near Seymour or Isedale or further south, we can use some folks. But anywhere, actually. And we have a training program, and we have tons of information online where you can see this stuff. And then we also, because we have a large concentration of observers in Champaign-Urbana, we also have a map that zooms down to the city level. This was from actually last July on the 22nd. And this is why we need lots of observers. Look at the difference in rainfall. Here, up around 74, we have 4,400. Down here, we got almost, well, we do have 2 inches. We have 2 inches, 2 1/4 inches. I had 2 3/4 inches up this way. No, that's not me. That's at the Eastern Urbana. So you can see how much the rainfall varies over a short distance in one day. That's why we need observers. And that's why, like more in Southwest Champaign and Northeast Champaign County, because we don't have anybody there. Well, this, you're talking what? We're talking Champaign-Urbana, and you know, sections there, 6, maybe 36 square miles, how much the rainfall varies. So it's a really interesting program. We have a lot of educational aspects. There's a special section for master gardeners. There's climate resources for master gardeners. I do a blog, Cobra's blog, which discusses various weather-related aspects. May or may not be related directly to Cobra's. So there's a lot of good information on there. If you're interested, you can talk to me afterwards, or you can go check the website if you want to join. It's a simple application to fill out, and we can get you going. So that's all you need to do. Training's available online. You do not need to attend a session. We don't have them all the time. A lot of good online resources, and then start making your observation. Thank you very much tonight for your attention. Questions? Yes.
Twice in my life, I've just had to stop whatever I was doing, observe the vivid violets, golds, greens, just all intertwining. And where do all those colors come from? Is it the same thing as a rainbow effect?
No,
or?
not necessarily. It depends. A lot of times the reds, you get it in the evenings or sometimes in the morning. Can be due to dust in the atmosphere. Last has to do with the angle of the sun in relation to what's in the atmosphere, either moisture particles or dust. If there's a volcano, let's say in Mexico, and a lot of that dust gets caught up in the upper level winds, frequently, long afterwards, we're going to have really spectacular sunsets because all that light reflects and refracts off those dust particles in the atmosphere. It's not unlike clouds. One of those, that winter photograph of, real orange photograph of the altocumulus clouds in the winter. It just happened to be the angle of the sun and the amount of moisture in the atmosphere caused that refraction of the light. So a lot of it has to depend on just having the right conditions. I mean, you typically don't see those. Usually the sun's at a low angle. You don't see them at noon when it's sunny typically. You might see green clouds, but that's more has to do with the amount of water in the clouds than anything with sunlight.
Yeah, but I'm not talking about a general greenish, bluish about it.
Mhm.
I'm talking about intertwined and sharp delineations between the colors and 4 or 5 colors all in the same area.
But not in the rainbow.
No.
Now, there are other different optical phenomena in the atmosphere, sundogs, which you can see the refracted colors in those. Typically, they're just bright colors. They're just bright white. But if the sun is at the right angle, you can see colors in those. And those are usually big spots on the other side of the sun caused by ice crystals and refraction. And depending on how thick the layer is and how much there is, you can actually break that up into colors. There are, at times, you can see when you get cirrus clouds in the atmosphere on a bright sunny day, you can see a sort of a rainbow effect in the upper level clouds. In the cirrus clouds, I've seen that several times, where it's not a lot, but you can definitely see the violet and the green and the red. And it's only lasts for a while because your position relative to that cloud and that cloud's position relative to the sun is refracting the light correctly. And that one little patch of clouds can actually show a rainbow effect.
It's all refraction.
Yeah, it's either because of ice crystals or dust in the atmosphere.
No ionization or anything like
No,
that going on.
Don't go marijuana.
No, at those levels, it's all due to the ice crystals. You know, we don't get any kind of ionization usually that low. The only thing that would cause any kind of ionization in that level of the atmosphere would be lightning from thunderstorms. And I didn't talk. I mean, you could have a whole session on thunderstorm features, but there's things called red sprites and blue jets, which they've discovered. They actually shoot out of the top of thunderstorm into space.
Into the
And the only reason they ever discovered these was because of high-speed photography.
Right.
But fascinating nonetheless, but not subject to this talk. Talking about stuff a little bit lower. But there's a lot of stuff that goes on, and some of it we don't understand yet either. Anything else?
Yeah, just a question about downbursts. About 25 years ago in Cone, we were awakened by what sounded like an explosion, and it was what we were told was a thunderstorm that essentially collapsed and just destroyed a building, sent debris up into the trees, and then it bounced and hit again about a half a mile down, and then bounced and hit again and caused more damage. I'd never heard of that.
Yeah, downburst is a general category. There's something called a microburst, which is much more concentrated, which sounds like what this is. But what happens is, you're going to get all that air going up in a storm. Eventually, it's going to cool off, and it's going to stop going up. And storms that move and are well developed have an updraft and a downdraft, so they tend to keep going. But that downdraft, depending on how high it comes from, is as that cold air descends, it accelerates. And it's concentrated on a spot on the ground. Think of it that way. It would be like I took this table and just opened up a canister of water and pulled out a lid off it. It fell straight down. It would spread out in every direction. But the worst of it would be right underneath where most of the force is. That's what a microburst is. And everyone wants to say, oh, that was a tornado. I got hit by a tornado. A tornado ripped down my house and all these trees. Well, to be honest, around here, most tornadoes don't do that much damage. I mean, they tend to be EF1s, EF0s, maybe EF2s. November was a real unusual situation here. But downbursts, thunderstorm downdrafts can cause far more damage. You can get 80, 90, 100 mile an hour winds in those that totally destroy things, especially underneath. Have you ever heard of heat bursts? Heat bursts is a similar situation that occurs out west. Very strange, but when you get thunderstorms out, the western U.S. in particular, you can get them here once in a while, but you'll get air from a thunderstorm that is dying, and it starts dropping through the storm, but as that air drops, it compresses and warms, and hits the ground, and it has the same effect. It can produce strong wind. But the most spectacular one I've seen, I actually experienced, I was in Scottsdale, and it was at night. Thunderstorm had gone up over Phoenix, and basically they don't move much. There's not much horizontal movement. So the thunderstorm developed, and it died. The heat burst came down. Winds did damage in Phoenix. The temperature where I was at in Scottsdale went from 103 to 115 in a half hour. at 11 o'clock at night. Because as air descends and compresses, it warms. And so it was already warm to begin with. So that air came down, and we didn't have much wind. There was some, but it was pretty spectacular. I mean, you could feel it when we were out at the pool, which, even at night, being in the pool at 103 isn't all that great. It's so dry. As soon as you get out, you chill down. But it was really unusual. And so heat bursts occur out west a lot, and they can occur from dry thunderstorms that basically don't. They may have a lot of virga. They don't actually rain out onto the ground. So similar type of phenomena, but here with thunderstorms, they tend to be very cold downbursts, and because that cold air sinks so rapidly, downdrafts coming down, it can cause a lot of damage. So if you get a very strong thunderstorm, a lot of your damage can be from microbursts. And some more spectacular microbursts have occurred up in Minnesota where the whole forest area is flattened. Seen some pictures of that. It's not tornadoes, but you get a strong downburst over there, and it just flattens everything out in a radial direction. And that's how they can tell a lot of the times whether or not damage is due to a tornado or straight line winds, is they look at damage patterns. They see trees oriented in different directions, and they see debris, especially from an aerial view, sort of in a circular pattern or has curvature to it. Probably was a tornado, but often they see debris just radially going out from one point. They know it's straight line winds. And they can do, like I said, they can do more damage than any tornado we've ever seen. So, but yeah, I think I remember that one. At least the news story about it. Anything else? Thanks again, everybody.